Hello there, welcome to another presentation on solving ordinary differential equations using the method of undetermined coefficients. In this case, we are continuing with our non-homogeneous case. You recall that we were dealing with equations of order n, where the right hand side f of x here is non-zero, in which case we are dealing with the non-homogeneous differential equations. Previously, we have looked at the right hand side being a polynomial function and being a trigonometric function, and we saw how we treat those kind of functions to get the particular integral. In this presentation, we're going to look at the exponential type of function on the right hand side of the equation. So our first example is as follows. It says solve the second order differential equation, and we see that the right hand side, which is the input side of the system, is an exponential function. So for solving this equation, like we saw before, the first step will be to set this equation as a homogeneous equation. I was just put the input to 0, then we have got d2 x dt squared plus 5 dx dt plus 6x equals to 0. This should be our initial step. So the next step will be in this case it's going to be m squared plus 5m plus 6 equals to 0. And clearly this equation can be factorized, this left hand side can be factorized as m plus 2 multiplied by m plus 3 equals to 0, giving our rows to be m equals to minus 2 or m equals to minus 3. In this case, we're going to get our complementary solution xt being equals to the initial undetermined coefficient c0 e to the power minus 3t plus the second coefficient c1 e to the power minus 2t. Now that we've got our complementary solution xc of t, we need to proceed and determine our particular integral. So that will be our step number 3 here. So determining particular integral, for that we let our trial solution be xpi, a function of t, equals to alpha e to the power minus 4t. What is important here when you are suggesting a particular integral, in this case, it is important that you keep the scaling factor of t here, minus 4t, the same as the one which appears on the right hand side of the function there. So we've got minus 4t there, and we've got minus 4t here. So our task here will be simply to find the alpha to get the particular solution for this differential equation. So having this as our solution, we then determine the first derivative xpi of t equals to minus 4 alpha e to the power minus 4t. And then the second derivative will be 16 alpha e to the power minus 4t. Now, since this is claimed to be a solution, it must satisfy the given equation. So we now take these two derivatives and substitute on the left hand side of the equation here, whereby we're going to get 16 alpha e to the power minus 4t plus 5 times the first derivative, which is minus 4 alpha e to the power minus 4t plus 6x, which in this case is going to be 6 times the trial solution, which is going to be 6 alpha e to the power minus 4t, equals to the right hand side, which we have as 3 times e to the power minus 4t. Simplifying, we've got 16 alpha e to the power minus 4t minus 20 alpha e to the power minus 4t plus 6 alpha e to the power minus 4t equals to 3 e to the power minus 4t. And we see that the left hand side, we get 2 alpha e to the power minus 4t equals to 3 e to the power minus 4t. And dividing both sides by e to the power minus 4t, we get 2 alpha equals to 3, and we conclude that alpha is equal to 3 over 2. In this case, now our particular integral x pi, a function of t, is equal to 3 over 2 e to the power minus 4t. The last step is to give our general solution, which in this case we're going to give as xg, a function of t, which is going to be equals to x complementary solution plus x particular integral, which in this case is going to be c0 e to the power minus 3t plus c1 e to the power minus 2t plus the particular integral, which is 3 e to the power minus 4t all over 2. In that case, we would have concluded finding our general solution. So since we're not given any initial conditions, we'll leave this as it is as a general solution. Now, moving forward, we take a similar example but with a slightly different challenge. This is actually initial value problem, because we're given initial conditions here for the value of function is 0 being 2 and the first derivative is 0 being 2. So what we're going to do here, for the solution, we set our equation as a homogeneous equation, which is 8 d2x dt plus 6 dx dt plus x equals to 0. Moving forward, we get our characteristic equation, which is going to be 8m squared plus 6m plus 1 equals to 0. And this also is an quadratic expression which is factorizable, and we can factorize this as 2m plus 1 multiplied by 4m plus 1 all equals to 0. Now we see that this will result in m equals to 1 minus 1 over 2, or m equals to minus 1 over 4. And then we give our characteristic solution, a complementary solution here. So now we give our complementary solution as xc of t equals to our initial undetermined coefficient c, e to the power minus half t plus c1 e to the power minus t over 4. That's our complementary solution. Now proceeding to the third step, we now determine the particular integral. Determine particular integral, again we let our trial solution be x particular integral, a function of t, equals to alpha e to the power minus t over 2. You notice that here again we're consistent with what we've got on the right hand side here, that we've got this independent variable scaled by minus 2. Differentiating this, we get minus alpha over 2 e to the power minus t over 2, which in this case, this is our first derivative of our suggested particular solution. And then the second derivative is equals to alpha over 4 e to the power minus t over 2. We know that the left hand side is 8 times the second derivative, which is that, which in this case we write here alpha over 4 e to the power minus t over 2 plus 6 times the first derivative plus x, which in this case is alpha e minus t over 2. And this is equal to the right hand side, which is 8 e to the power minus t over 2. Now simplify the left hand side here, we've got 2 alpha e to the power minus t over 2 minus 3 alpha e to the power minus t over 2 plus alpha e to the power minus t over 2 equals to 8 e to the power minus t over 2. In this case, when you simplify the left hand side, we see that it gives us 0 equals to 8 e to the power minus t over 2. And we all know that the exponential function is never equal to 0. So what we get here is simply a contradiction. And because of that, we are forced to reject this trial solution which was suggested here, because mathematics is a science which is clean of contradiction. So in this case, we conclude that this is not a suitable trial solution, and that you must note it is caused by the fact that minus half is actually the zero of the characteristic equation, and again minus half here is the scaling factor of the argument of this exponential function here. So always when that happens, when a factor appears as a 0 and also appears as the scaling factor here for the exponential function, we are always going to get this contradiction. In this case now, the question is, how do we go about avoiding this kind of a situation? We simply need to suggest another trial solution which is different from this one. Now, what if we would like to understand this trial solution here? we could also write it as alpha t to the power 0 e to the power minus t over 2. So in this case, we'll say we failed here with the t to the power 0. So the natural thing to do is to try a t to the power 1. We're going to say here, let the trial solution be x particular integral function of t equals to alpha t e to the power minus t all over 2. Now having that, we can now differentiate, find the first derivative, which in this case we're differentiating a product, and in this case is going to be alpha e to the power minus t over 2. Having differentiated the function, let's say y is equal to t, then plus alpha t e to the power minus t over 2 multiplied by minus half, which gives us alpha e to the power minus t over 2 minus alpha t e to the power minus t over 2 all over 2. That will be our first derivative. Our second derivative, we note that here we're going to differentiate this, and here we're going to differentiate a product again. So there we're going to have minus alpha e to the power minus t over 2 divided by 2 minus alpha e to the power minus t over 2 divided by 2. Now as we differentiated this t here, plus alpha t e to the power minus t over 2 divided by 4. This is after multiplying by the derivative argument here, which is minus half. We get here the denominator being 4. And then we have got here our second derivative. Now substituting in the left hand side of the equation, we're going to get here 8 multiplied by minus 2 alpha. We're going to get here minus 8 alpha e to the power minus t over 2 plus 2 alpha t e to the power minus t over 2. That's the first term of the left hand side of the differential equation. Plus 6 times the first derivative. In this case, we're going to get 6 alpha e to the power minus t over 2. Multiplying, we're going to get minus 3 alpha t e to the power minus t over 2 plus x, the solution, which is simply alpha t e to the power minus t over 2. And this is this is claimed to be a solution. This must be equal to the right hand side, which is 8 e to the power minus t over 2. Now let's simplify the right hand side. We've got like terms here, 2 alpha t and 3 minus 3 alpha t plus 3 alpha t, and we see that these terms, they simplify to 0. And on the other hand, here we've got minus 8 plus 6, which gives us minus 2 alpha e to the power minus t over 2 equals to 8 e to the power minus t over 2. And dividing both sides by e to the power minus t over 2, we get minus 2 alpha equals to 8, where we conclude that alpha is equals to minus 4. So then we've got our particular integral x pi of t is equals to minus 4 t e to the power minus t over 2. And then now our general solution xg is going to be equals to our initial undetermined coefficient is 0 e to the power minus t over 2 plus c1 e to the power minus t over 4 plus the complementary solution, which is minus 4t e to the power minus t over 2. Now this is our general solution, but we're given initial conditions that x at 0 is equal to 2, and the derivative of the function x at 0 is also equals to 2. So what we're going to do here, x at 0 equals to 2 implies that c0, when you substitute here, you get 1 times c0, that plus c1, substituting that way, is equals to 2. because here when you put 0, this is going to vanish. And now we've got one equation there which you're going to keep, and then differentiating, getting the first derivative, dxt, this will give us minus c0 over 2 e to the power minus t over 2 minus c1 over 2 multiplied by e to the power minus t all over 4 minus 4 e to the power minus t over 2 plus 2t e to the power minus t all over 2. That will be our derivative. But now we're told that when you evaluate the derivative is 0, we still get 2, which in this case, this term and this term, e to the power 0 here will give us a 1 and a 1 there. Then we're left with minus c0 over 2 minus c1 over 4 minus 4 times 1, that is equals to 2. In this case, simplifying this, let's say multiplying both sides by 4, we get minus 2c0 minus c1 minus 16 equals to 8, which gives us minus 2c0 minus c1 equals to 24. So now we've got equation 2 here, which involves c0 and c1. Now, taking the two equations simultaneously, we've got the two equations which you can solve by elimination. In this case, we can simply add the two equations. We get minus c0 equals to 26, whereby c0 is equal to minus 26. Now, if c0 is equal to minus 26, substituting in equation 1, we've got minus 26 plus c1 equals to 2, which gives us that c1 is equals to 28. So now, writing our particular solution, or our unique solution given the initial conditions, is going to be x, a function of t, equals to minus 26 e to the power minus t over 2 plus 28 e to the power minus t over 4 plus our particular integral, which is minus 4t e to the power minus t over 2. And that concludes the exercise. Now, what is important to highlight is what we did when we got a contradiction at this stage. We simply need to do it step by step. From here where we're at t0, t to the power 0, we just increase this by 1 and go to t power 1. So if this was repeated, the solution was repeated twice, as you're going to see in this upcoming example, you will see that t to the power 1, like we suggested here, again is going to fail. And let's see what's going to happen. Then we conclude this presentation. Now we're given here the equation d2 dx dt squared plus 2 dx dt plus x equals to 2 e to the power minus t. Now, for a solution, initial step, we set the equation as a homogeneous equation, followed by extracting the characteristic equation, which is m squared plus 2m plus 1. So it's m squared plus 2m plus 1, and we see that this factorizes as m plus 1 squared equals to 0, whereby we conclude that m is equal to minus 1 twice, and therefore our complementary solution is going to be initial undetermined coefficient C0 e to the power minus t plus C1 t e to the power minus t. I hope at this stage you still remember how you handle repeated real roots like this one. And then next step, we determine our particular integral. Then we let the trial solution be. We start by using x particular integral equals to alpha e to the power minus t. Now differentiating, we get minus alpha e to the power minus t, and in the second derivative we get alpha e to the power minus t. Now substituting on the left hand side of the equation, we should have the second derivative, which is alpha e to the power minus t plus minus 2 alpha e to the power minus t plus x, which is alpha e to the power minus t, equals to the right hand side, which is 2 e to the power minus t. Now simplifying the left hand side, we can see clearly that we get 0 equals to 2 e minus t. And again, this is a contradiction, which suggests that you shouldn't accept this as our trial solution. And again, we recall that here I said you could write this as alpha t to the power 0 e to the power minus t. And then since we fail with that, we then let the trial solution be x particular integral equals to alpha t to the power 1 e to the power minus t. Now coming up with the first derivative here, we're differentiating a product, which is going to be alpha e to the power minus t plus alpha minus alpha t e to the power minus t. That will be our first derivative. Second derivative, that will be equals to minus alpha e to the power minus t minus alpha e to the power minus t plus alpha t e to the power minus t, and then substituting in the equation, simplifying and substituting in the equation, we get here minus 2 alpha e to the power minus t plus alpha t e to the power minus t, which is our second derivative, plus 2 times the first derivative, which gives us 2 alpha e to the power minus t minus 2 alpha t e to the power minus t plus the solution, which is alpha t e to the power minus t, equals to the right hand side, which is 2 e to the power minus t. Simplifying the left hand side again, collecting the like terms, minus 2 alpha plus 2 alpha, they give us 0. And then alpha t e plus alpha t e, they give us 2 alpha t e minus 2 alpha t, they give us 0. Again, we get here 0 equals to 2 e to the power minus t, which is again a contradiction. Again, we're forced to reject this. So now we need to continue. We continue by increasing the power of t here by 1, which then suggests that we let the trial solution be x particular integral equals to alpha t squared e to the power minus t. And I would like to highlight the fact that our 8t squared here and the root minus 1 was also repeated twice. And then let's see what's going to happen. Now, having this trial solution, differentiating x pi prime, differentiate this product, we're going to get 2 alpha t e to the power minus t plus minus alpha t squared e to the power minus t. That will be our first derivative. Now, second derivative, differentiating this, we've got 2 alpha e to the power minus t minus 2 alpha t e to the power minus t. We finished differentiating this product. And differentiating here, we're going to get minus 2 alpha t e to the power minus t plus alpha t squared e to the power minus t. Substituting these derivatives on the left hand side of the equation and simplifying these terms here, we got 2 alpha e to the power minus t minus 4 alpha t e to the power minus t plus alpha t squared e to the power minus t. That's our second derivative there. Then multiplying the first derivative by 2, we've got 4 alpha t e to the power minus t minus 2 alpha t squared e to the power minus t plus the solution, which is alpha t squared e to the power minus t, all equals to the right hand side, which is 2 e to the power minus t. And now, simplifying the quadratic terms, you see that this and that, they give us 2 t squared e to the power minus t minus that, we get a 0. And then minus 4 alpha t plus 4 alpha t times the exponential, they also give us 0. And then we're left with 2 alpha e to the power minus t equals to 2 e to the power minus t. And dividing this by e to the power minus t, we get that 2 alpha is equals to 2, whereby we conclude that alpha is equals to 1. So in this case now, we conclude that our particular integral is simply 1 times t squared e to the power minus t. So in this case now, we see that when we arrived here at the end here, we didn't have any contradiction, and we were able to solve for alpha and get our particular integral. Now, our general solution now is going to be xg function of t, which is equal to the complementary solution, which was c0 e to the power minus t plus c1 t e to the power minus t plus t squared e to the power minus t. At this stage, let's highlight something here. In the first equation, where the root of the characteristic equation appeared as the scaling factor on the right hand side, it was the scaling factor was minus half, and the m was also equals to minus half. In this case, this root was appeared only once, and the trial solution which worked here was an xpi, the function of t, equals to alpha t to the power 1 e to the power minus half t. And now in this case, where the scaling factor of on the right hand side of in the exponential function was minus 1, and the root m equals to minus 1 was a repeated root. Now it occurred twice. Then the trial solution which worked was xpi equals to alpha t squared e to the power minus t. So what I'm suggesting, in my example, I started by trying x alpha t to the power 0, then followed by x alpha t to the power 1 until we get to 2 here. I was just doing that to show you what you could get. But in practice, when you see the root appearing once, then immediately suggest your solution to have an alpha t to the power 1 and multiply by the same kind of an exponential function with the same scaling factor here. And then if you see the root appearing twice or thrice, then the power of t here must be the same as the number of times the root is repeated. Like here is repeated twice, the power of t here is twice. I hope you understand that. And with this explanation, I believe you are ready to tackle these kind of problems, which is actually a different types of problems where you're going to get repeated roots, non-repeated roots, and so on. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Wells Fanemsi.